Hey guys, and welcome to 2.2. We're going to look more at functions and their graphs today. So in 2.2, there's a lot of conversation about symmetry. So let's talk about that. If you take a negative x and plug it into f of x, and it spits out your original function, that means you're symmetric to the y-axis. Okay, if you plug in negative x to the original function and you get out the opposite of your original function, like so, then you're symmetric to the x-axis. Okay. And then also while you're looking at the graph, there's this whole conversation of like, I mean, is it increasing? Is it decreasing? Is it constant? If or number two, if you have a graph that has some hills and valleys in it, peaks and valleys, what is your do you have a max? Do you have a min anywhere? Well, we can figure this stuff out. Well, number one, let's start the conversation here. When you're trying to figure out is something, or when they're asking you, when is it increasing, when is it decreasing, when is it constant, you're only looking at the x values. Okay. And you look at it from least to greatest, from left to right. Okay, so if you look at the graph here on number one, it's decreasing from the time you get onto the graph all the way to x equals 2. Right here is the pivot point. Now, if you know anything about interval notation, sometimes you use concede, sometimes you use brackets, right? You don't use anything but parentheses when you're answering these questions. When it's increasing, like, because again, it's not increasing or decreasing at a given point. It's decreasing through a point or approaching a point. It's and then if you move past x equals 2, it flatlines. It's a constant, right? So in this case, it's not increasing ever. So this would be none. It's decreasing from negative infinity because it goes off the graph. It comes onto the graph already decreasing, and then it comes down and it stops decreasing at x equals 2. And then it's constant on the other side to positive infinity, right? So this is what I'm talking about. There's no brackets or anything like that. It's not increasing, decreasing, or constant at 2. And as you approach 2 from the right, it's decreasing. As you leave 2 and approach 2 from the left, then it is constant. Okay. Now, so that's one thing. And a lot of these problems, they could ask you for all three. They could only ask you for one. So just be mindful of that and answer what the question is. Okay. So if you look over this graph that they give you, this is the function that it belongs to. When is it a relative max, relative min? So any kind of cubic graph is going to go on forever in both directions. So it's relative because it increases without bound and decreases without bound. It doesn't have a true max or a true min. But if you look in this window of time, which is what this entire graph is doing, it does have a peak and a valley that we can look at. So relative means like a local max or a local min. It's not absolute. Okay, well, I want to know where is the max, where's the min? Well, the max is right here. The min is right here. All right, when is that? This is when x equals -1. This is when x equals +3. Okay, so that's your max and min are both ordered pairs. So in order to figure out what the rest of this is, you need to crunch your numbers. All right, so if I plug in -1, that's going to be 2, -1, cubed minus 6, -1 squared, minus 18, -1 plus 7. It's going to be -2 minus 6 plus 18 plus 7 minus 8 plus 25. It's going to be 17. So -1 comma 17. So you plug in your x value into your equation and it spits out your y value. Okay. And that's going to give you your entire point for your relative max. And then you already know that x, when x is 3, you have a relative min. You do the exact same thing to figure out what the y value is here. You plug 3 in for x, you get an answer, and it's going to be -47. Okay. So these are your two answers here. Okay. Now, number 3. This is a word problem. And it happens to be like a systems of equations problem, which means I have two linear equations. I'm going to use the two of them to solve this problem. So it says that you invested $14,000 in two accounts, paying 2% and 8% respectively, annual interest. If the total interest earned for the year is $580, how much did you put in each of them? Well, here you need to let x be something and y be something. So let's let x be the 2% account and the y be the 8%. Okay, and if that's the case, it's going to be x plus y. These are the amounts. X plus y is 1,400, or sorry, 14,000. And then I put so much in the 2%, and you have to change to a decimal, so much in the 2%, and then so much in the 8%. And my total interest for the year was 580. Okay, so that's my equation. Now I need to solve this system of equations. And I can do this simply by solving this one for y, and this is going to be y equals 14,000 minus x. Okay, but that allows me to sub in. So I got 0.2 x plus 0.08 y. I know what y is now. It's going to be 14,000 minus x equals 580. Now, the reason I have to do this is because when you have two variables that you don't know, you can only solve for one or the other, but you leave things in generic terms. Uh, you can't get a true answer unless you have one variable. And so doing the system equation, the method I used is called a substitution. You can use substitution, you can use elimination, or you can use graphing. Um, but here I use substitution, and now by doing that, I created an equation that only has one variable, and now I can solve for x. So this is going to be 0.2x plus 0.08 times 14,000 is going to give you 1120 minus 0.08x equals 580. Okay. 0.02x minus 0.08x is going to be negative 0.06x. 1120 equals 580. Okay. So it's going to be negative. I'm going to subtract the 522 of the 1120 to the other side. It's going to give me negative 540. So that's going to give me, when I divide, x equals 9,000. Well, this is what y was 14,000 minus x. I now know what x equals. So y is going to be 14,000 minus 9,000. Okay, so here's what we got. We got 9,000. That's 2%. We have 5,000. It's 8%. So that's how I split the money. And this is how I got what I got for the year, $580. Okay, so that's how you do that. All right. Now, when it comes to any graph, one of the greatest tools in your tool bag is symmetry. It doesn't have symmetry. If it does, what kind of symmetry? Right? You could have x-axis symmetry, y-axis symmetry, or origin symmetry. Origin is when you essentially have both x and y, and it flips over the origin. Right? Or another way to think about it is it rotates 180 degrees and falls back on itself. Okay, so here's one way to do that. So think about a graph. Think about a graph. If I have a point that's xy, everything's positive in the first quadrant. If I flip it over the y-axis, that means I have a point over here. That'd be negative x, y. So this would give me y-axis symmetry. So if I want to know if this has y-axis, something has y-axis symmetry, I plug in negative x. Also, if I want to know something has x symmetry, I plug in negative y for the same reason. And then if I want to know something has origin symmetry, I plug in both negative x and negative y. So let's play with this a little bit. So if I plug in negative x, y squared plus 17, there's no way I can get back to my original equation. That's what I'm trying to do. I want to plug in the negative x with the negative y, apply the equation to it, and I get my original back. If I do, then it is symmetrical in that with respect to whatever axis I'm trying out. In this case, it's not respective to y. All right, so that doesn't work. Let's try this one. X equals, open parentheses, negative y squared plus 17. All right, I can easily get, once I apply the square, I can easily get my original back. So this is going to have x-axis symmetry. Again, because I plugged in negative y, it has x-axis symmetry. Okay. Now, over here on 5, let's say let's plug in negative y. Negative y equals 5x plus 8. Doesn't have it. Let's see. Y equals 5 times negative x plus 8. That's not going to work either. Let me do both. Let's see. I get negative y equals negative 5x plus 8. Right? If I divide negative from both sides, it's going to be y equals 5x minus 8. So close. If that 8 didn't change its sign, then this would have been origin symmetry. But this doesn't have anything. So I tried everything. This is no, this doesn't have symmetry at all in regards to the axes. So number 6, I plug in negative x. It's the fourth, y to the fourth plus 3 negative x, y 6. Okay, that's going to be x to the fourth, y to the fourth plus, um, excuse me, minus 3xy equals 6. That's very close to what I originally started with, but it's not. So I don't have y-axis symmetry. Let me try negative y. So I got x to the fourth, negative y to the fourth plus 3x negative y equals 6. It's going to give me negative, sorry, it's going to give me x to the fourth, y to the fourth minus 3xy equals 6. Once again, it doesn't get me there. Let me try both. All right, I have negative x to the fourth, negative y to the fourth plus 3 negative x negative y equals 6. Okay, so because of the way this problem is set up, the even powers are going to take care of my negatives in the beginning. But the problem before was that I needed a second negative to cancel out with. But when I introduce both negative x and a negative y, then my first part of the equation is already taken care of. But that wasn't a problem. But now I have negative x, negative y. It's going to leave me with positive 3xy equals 6. That's what I wanted. I wanted the original show back up. It finally did. But it only happened once I plugged in negative x and negative x and a negative y. So since it took that, this has origin symmetry. See? Okay, when it comes to symmetry, there are a separate conversation we have. There's x-axis symmetry, y-axis symmetry, and origin symmetry. But there's also the conversation of whether or not a function is even or odd. And even is if a function has y-axis symmetry, it's even. If it has origin symmetry, it's odd. And when we're talking about is a function even, odd, or something like that, x symmetry has no part in that, because if x has symmetry, if it has x symmetry, then it has, that means the x's are going to repeat. Okay, and we can't have that, which means it's not a function. So there is the x-axis symmetry, but those don't have they are not a function. So similarly, you can do it graphically or you can do it algebraically. We're going to start with the algebra part of it. On 7, one of the things I like about the even odd or neither problems is it's a simple test that I complete. And I can figure out real quick if it's even, real quick if it's odd, or even real quick if it's neither. So let's talk about this. I'm going to plug in a negative x and see what I get. And if I can get my original out, then I have an even function. So let's see what I get. Use that. That's going to be negative x to the fifth minus x. Or that should be that should be plus 6. Okay, that is not my original, so it's not even. Okay, let's take another look. If I can take a negative out of the, like a GCF of -1 out, do I get my original back on the inside? So that's going to be x to the fifth minus 6. Well, it turns out I do. If I can take a GCF, it's not even, because when I plugged in the negative x, I didn't get my original back. All right, but when I did plug in a negative x, and after I applied the function and then factored out a -1, it's a negative times my original, which is essentially the opposite of my original. If that happens, this is odd. So this function is odd. Number 8, I'm going to do the same thing. The first test to see if it's even. I'm going to plug in the negative x squared minus 2 negative x. Okay, I'm going to plug that in. That's going to be x squared plus 2x. Okay, that's not my original. So I'm going to factor out a negative and see what it gives me. That gives me negative x squared minus 2x. All right, that is also not my original on the inside. So I plug in a negative x to see if it gives me my original. It doesn't. So I factor out a -1, and I'm hoping that inside the parentheses, so I have a negative on the outside, and inside the parentheses, I'm hoping my original shows up. In this case, it doesn't. So it's not even, it's not odd, so it must be neither. So like I said, this is the beautiful thing about even odd or neither is it's a quick test. And even odd, you'll know that real quickly, or you'll know if it's even really quickly, and then just as quickly you'll know if it's odd. And if it's not either one, then it's just simply neither. Okay, now a lot of times in algebra, we're given things with multiple variables, and sometimes, like I mentioned earlier, that if you have more than one variable that's unknown, you can't get a true answer. But you can rearrange the problem so that when you do get those other pieces of information that just show up, so that when you do get those other pieces of information, you can just plug them in. You don't have to do the moving stuff around. You just plug them in and collect your numbers. So on number 9, I got this capital J equals capital F plus capital R, sorry, capital F R T. And I'm going to solve this thing for T. So I want to get the T term by itself first. So I'm going to subtract the first F. That's going to be J minus F equals F R T. And then the T term right now is F times R times T. So I'm multiplying, and I undo multiplication through division. So I'm going to divide by everything that's not T. Okay. So there's that. There's that. And now that goes away. And I'm left with T equals J minus F over F R. And that's it. Now, technically, my T was on this side of the equal sign. And so you may be thinking that I should have put T on this side. All right, whether T is on this side or on this side, it means the exact same thing. So don't get hung up on that. Okay, so there's that. Number 11. Sorry, number 10. This is what we call a piecewise function, where on part of the domain, it acts like one graph, and another part of the domain, it acts like another graph. And you can have a minimum of 2, otherwise it's just a function. Or you can have an unlimited number of functions uh, over your entire domain, because your domain is negative infinity to infinity. So you can carve or chop that up in any number of ways you want to. So here, you just want to do a couple things. First of all, I have a -4 here. So which function do I use? Do I use the first one, 3x plus 5, or the second one, 4x minus, or 4x plus 7? Well, -4 is less than 0. So I'm going to plug in -4 in the first one and see what I get. So that's going to be -12 plus 5, which is -7. Okay. Same thing on 0. All right. This is less than 0, but it's not equal to. I need equal to. So I'm going to use the second one. Okay. So 4 times 0 plus 7. All right. The first part of that's going to go to 0. So this is just going to be 7. And then similarly, this is greater than or equal to 0. So 1, we're going to plug into the second one as well. So it's going to be 4 plus 7, which is 11. Okay. There you go. Now, on 11, 12, we're going to wrap this thing up talking about this thing called the difference quotient. Now, if you know anything about slope, which we're going to really get into in the next lesson, it's all about the rate of change, or the average rate of change. And the difference quotient itself is actually used a lot in pre-calculus or calculus. So if you have plans to go further than this class, you'll see this a lot. It's a simple formula: f of x plus h minus f of x. F of x is already your original, x plus h is your difference. And so, real quick, your slope formula is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Well, if you redefine this a certain way, you get your difference quotient. So this is it's a form of the slope formula. But how do you use this? That's probably the most important thing. Okay, well, again, your original is f of x. So let's do this. We have f of x. Let's do f of x plus h. You already have f of x. F of x plus h, I'm going to plug in an x plus h everywhere I see an x. All right, so that's f of x plus h. So now I'm going to subtract that from my original. All right, so I got negative, and I'm going to distribute this. This is going to be -4 minus 4h minus my original. So minus 4x over h. Okay, now let's distribute that. It's going to be -4x minus 4h minus, or plus 4x over h. Well, as you can see, you have -4x and positive 4x. Okay, so that leaves me with -4h and h. Well, I can get rid of those h's and I'm left with -4. Okay, there's that. This is actually, like I said, this is a calculus topic, and it's a piece of the definition of a derivative, which is one of the main pillars of calculus 1. So if you have aspirations to go into cal 1, derivatives is not much more than slope. So if you can handle slope, you can handle cal 1. Okay, number 2, same thing. Let's find x plus h. Okay, that's going to be x plus h squared minus 4 x plus h plus 9. It's going to be x squared. This is the same thing as x plus h times x plus h, which is going to follow a certain pattern of x squared plus 2xh plus h squared. Okay, and then it's going to be minus 4x minus 4h plus 9. All right, so I'm ready to plug this in. It's going to be x squared plus 2xh plus h squared minus 4x minus 4h plus 9. Oops, forgot. Minus my original. So x squared minus 4x plus 9 all over h. Okay, so let's clean this up. We have x squared plus 2xh h squared minus 4x minus 4h plus 9 minus x squared plus 4x minus 9 all over h. Okay, so I have a plus 9 and a minus 9. I have a minus 4x and a plus 4x. I have an x squared and a minus x squared. Right, so my original took away all this stuff. And so this is going to leave me with, just going to rearrange some terms. It's going to be h squared plus 2xh minus 4h over h. Now, you should notice that everything has an h in it. So let me factor that out. That's going to be h plus 2x minus 4. And there's what? And this. The leftover is going to be my answer. Okay. Yeah, guys. I hope that wasn't too overwhelming for you. If you have any questions, please reach out, and I will see you in the next video.